Hello everyone, welcome to my class. Today we will learn inverse Laplace transform. First, quick preview. In this lecture, we will define inverse Laplace transform and investigate some of its properties. We will provide some techniques which are useful while computing the inverse Laplace transform. We then find the inverse Laplace transform of some transformed function using Laplace transform table. We also solve second-order linear differential equations with constant coefficient using the Laplace and its inverse methods. Note that there is usually more than one way to invert the Laplace transform. Now, let me first recall the Laplace transform. The Laplace transform of functions f of t, where t opens represents the time, is defined as Laplace transform of f of t equals to the improper integral 0 to infinity and then exponentially decay term e to the power negative st times little ft dt. Which function we are computing the Laplace transforms? We multiply by e to the power negative st and take the improper integrals with respect to dt. Then after computing the improper integrals with respect to t, this gives us a function of s which we denote by capital F of s. So capital F of s is the Laplace transform of little ft. Great. Now let me define inverse Laplace transform. Let capital F of s is the Laplace transform of little ft. Then the inverse Laplace transform of capital F of s is denoted and defined by Laplace, that's for the inverse. So inverse Laplace transform of capital F of s equals to little ft, and we call little ft the inverse Laplace transform of capital F of s. And we denote the corresponding pairs, little ft and capital F of s, as a transform pair. So in here, this little ft is the inverse Laplace transform of capital F of s, and capital F of s is the Laplace transform of little ft. Let me visualize. So the Laplace transforms carries the function of t in length and frequency domain, and then the inverse Laplace transform carries the frequency domain, the frequency or the transform functions, and lands back on time domain. So the inverse Laplace transform is a linear operator for given transform functions capital F and capital H. The inverse Laplace transform satisfies the linearity property. This is the linearity property. Let me scroll down. Some quick side note: most of the Laplace transform have quotient form, so to compute the inverse Laplace transform, some of my techniques are as follows: algebraic manipulations, complete the square, partial fraction expansions, and Laplace transform table lookup. So good. Now let's use these ideas and to compute some of the inverse Laplace transform of some transform functions. So let's start. Example 1 says find the inverse Laplace transform of 5 over s plus 1 over s to the power 4 minus 3 over s plus 8. So the solutions, the next step, we know the inverse Laplace transform is a linear operator, so we can send this inverse Laplace transform to each of the terms inside this bracket. So the next step, inverse Laplace transform of 5 over s plus inverse Laplace transform of 1 over s to the power 4 minus inverse Laplace transform of 3 over s plus 8. Then by looking the Laplace transform table, we can pull the 5 outside, and inverse Laplace transform of 1 over s is 1, so 1 times 5 is 5. We use the formula number 1. And then for the second term, we use the formula number 3. The formula number 3 says Laplace transform of t to the power p over p factorial is 1 over s to the power p plus 1. So in our case, let's put p equals to 3. So 1 over s to the power 4. So the inverse Laplace transform of 1 over s to the power 4 becomes t to the power 3 over 3 factorial, which is this one. Then minus, then the Laplace transform of, inverse Laplace transform of 3 over s plus 8 is e to the power negative 8t. We use a formula number 11, which says Laplace transform of e to the at is 1 over s minus a. So the inverse Laplace transform of 1 over s minus a is e to the at. Put a equals to negative 8. Right. Another fact, if our transform function is not in a recognizable form in the Laplace transform table, then transform it by an algebraic manipulations. Let me scroll down and let's do one example explaining this little fact. That's better. Example 2. Find the inverse Laplace transform of 3 over s to the power 4 plus 5 over s squared plus 3. So in the solution, inverse Laplace transform is linear, so you can compute the inverse Laplace transform of each of these terms. So this expression here. So the first one, 3 times inverse Laplace transform of 1 over s to the power 4. So this one fits to the Laplace transform table. The next term, which is, I can pull 5 outside. Then we have inverse Laplace transform of 1 over s squared plus 3. And now to apply this formula here, the formula number 7, I need to multiply by radical 3 and divide by radical 3. Because in formula 7 says Laplace transform of sine kt, k is constant, is k over s squared plus k squared. So the inverse Laplace transform of k over s squared plus k squared is sine of kt. So by comparing this to this one, I have s squared plus radical 3 squared in my denominator. So to apply this formula, I do need a k term on my numerator, which is radical 3 for our case. So I multiply by radical 3 and divide by radical 3. So we manipulate here. Then we apply the formula. In the next step, 3 inverse Laplace transform of 1 over s to the power 4 is t cubed over 3 factorial. Then plus, the constant is 5 over radical 3. And the inverse Laplace transform of radical 3 over s squared plus radical 3 square is sine radical 3t. Great. So in the next step, we just cancel this 3 factorial to 3, so the 2 left, because 3 factorial is 3 times 2 times 1. We simplify here. Awesome. Let's move on. Let me scroll down here. Example 3. Find the inverse Laplace transform of 1 over 4s plus 1 minus 3 over s squared plus 2s plus 10. Answer, since inverse Laplace transform is a linear operator, so we send the inverse Laplace transform to inside here. And now for the first term here, we don't have the formula for finding inverse Laplace transform of 1 over 4s plus 1, so we pull the 1/4 outside, or we factor the 4 out from the denominator. We manipulate here. So then this denominator becomes s plus 1 over 4, and then we can apply the formula. And for the second term here, inverse Laplace transform of 3 over s squared plus 2s plus 10. so we need to factorize the denominator. So we use the completing this square, then we write inverse Laplace transform of 3 over the s squared plus 2s plus 10, using completing the square becomes s plus 1 squared plus 9. Then we use a formula. So for the first one, this is 1/4, this is e to the power negative t over 4, and for the second one, the minus as it is, inverse Laplace transform of 3 over s plus 1 squared plus 9, which is the formula here, is the formula number 18. So this 7 is for the first one. Let me go to the formula here. The inverse Laplace transform of k over s minus a quantity square plus k square is e sine kt times eat. So for our case, now our a is minus 1, k is radical 9, means 3. So this fits to this table. So we apply this formula. So this gives us e to the power negative t times sine 3t. Awesome. Let's move on. Example 4. So we use the completing the square technique here. So next, the example is about using partial fraction. Let me scroll down. That's better. Example 4. Find the inverse Laplace transform of the fraction s over s cubed plus 4s. So here, the transform function is s plus 1 over, you factor the s out, s times s squared plus 4. Then using partial fractions, and the denominator I have linear factor and quadratic factor. So using partial fraction technique, this equals to constant over s plus the linear terms bs plus c over quadratic term s squared plus 4, where a, b, c are constant to be determined. Then here we take the LCD, s times s squared plus 4, so we multiply a by this denominator s squared plus 4, and plus b s plus c, we multiply by this s, which is here. Now we are multiplying both sides by LCD to focus on the numerator. So that means we cancel the denominator, so then we have s plus 1 equals to a times s squared plus 4 plus bs squared plus c. There are many ways to compute the value of this constant a, b, and c, but I use this comparison. So I compare coefficient of s, which is 1, which is c, so we found c equals to 1. Coefficient of s squared, left side is nothing, 0, right side is a plus b. Then I have this relation, a plus b equals to 0. And in the next, I use s equals to 0, so the left side is 1, right side is a times 4, this term 0, this term 0. So I have from this relations a equals to 1/4. I use this value back on the second relation, so that gives me b equals to negative 1/4. So we found the value of a, b, c. A is 1/4, b is negative 1/4, c is 1. Thus, our f of s equals to s plus 1 over s times s squared plus 4 equals to, let's put a, b, c value back here. So 1/4, 1 over s, and then we put the b value, then c value, and we simplify. So now we are in here. So then next, let's take an inverse Laplace transform. Let me scroll down. Then we take inverse Laplace transform. So the left side, inverse Laplace transform f of s equals to, so 1/4 inverse Laplace transform of 1 over s, which is 1, minus 1 over 4 inverse Laplace transform of s over s squared plus 4. So this applies the formula. So this will be cosine 2t. Then here now I need to manipulate again. 1 over s squared plus 4. I need a constant on the top, so that its inverse Laplace will be sine of 2t. So let's multiply by 2, divide by 2, which I did here. And then the last one, to the left side, this is little ft equals to 1/4, this is 1, minus 1/4 times inverse Laplace transform of s over s squared plus 4 by formula number 8 gives us cosine 2t, then plus 1/2 inverse Laplace transform of 2 over s squared plus 4 by formula number 7 gives us sine of 2t. Great. Now let's move on. Now next, let's use Laplace transform and inverse Laplace transform to solve the differential equations initial value problem. First idea, first take Laplace transforms both sides of given differential equations. That gives you an algebraic equations in transform domain, or the algebraic equations of capital Y of s. Then solve for capital Y of s algebraically in the transformed domain, means find the solutions, and then recover that solutions by taking inverse Laplace transform in time domain. So that's the idea. We are kind of making a loop here. So here is a time domain, applying Laplace transform goes to the frequency domain, and we find the solution in the frequency domain, and we recover the solution in time domain by taking inverse Laplace transform of that solutions. I hope you understand this technique here. So now let's do example. Let's do solve the first order linear differential equations first, and then we'll talk about second order later. So solving the first order linear differential equations with constant coefficients. Example 5. Solve y prime. This prime is for, that's a time derivative. Y prime plus 3y equals to 9. Initial condition y0 equals to 2. Solution. Take Laplace transforms both sides. So Laplace transform of y prime plus 3y equals to Laplace transform of 9. We know Laplace transform also a linear operator. So Laplace transform of y prime plus 3 times Laplace transform of y equals to Laplace transform of 9. So then here, so Laplace transform of so Laplace transform of y prime by this derivative formula, this is s times capital Y s minus little y0 plus 3, this is Laplace transform of y, which is capital Y s, equals to Laplace transform of 9 is 9 over s. Then put initial conditions, so y0 equals to 2, and let me go down here. Then I can pull the Laplace transform of s, or that means capital Y s, I factor out. Then this gives me s plus 3 here, and equals to, this is the initial conditions, negative 2, pull to the right side, positive 2, and plus I have 9 over s on the right side. Great. And then in the next step, let's divide both sides by this s plus 3. So we divide in this line, ys equals to 2 over s plus 3 plus 9 over s times s plus 3. Let me scroll down here. Oh, I don't know. This is also here, and this side also there. So I think we are here, means we are here. We are here. Okay, so now, so then use partial fraction technique for these fractions. So the first is just, you don't need to do anything, 2 over s plus 3 and plus, so this becomes 9 over s times s plus 3 equals to a over s plus b over s plus 3, because both of these are linear factors, so we just use constant a and b, and it happens to be is 3 and b is negative 3. It's just by observations. You can check quickly. Let's forget the first one from the second one. Yes, from second and third. 3 times s plus 3 minus 3 times s. 3 times s cancel, so 3 times 9, which is here. Awesome. Then let's simplify. This is 3 over s minus, this is 1 over s plus 3. And finally, take the inverse Laplace transform. So the left side is capital Y of s. So inverse Laplace transform of capital Y of s is little yt equals to excuse me, inverse Laplace transform of 3 over s is 3 minus inverse Laplace transform of 1 over s plus 3 is e to the power negative 3t. Great. Let me scroll down. Now let's talk about solving the second order linear differential equations with constant coefficients. First, let's have some discussion. So we have a second order linear differential equation with constant coefficients. A double prime plus by prime plus cy equals to little ft. Initial conditions are y0 equals to k0, y prime 0 is k1. Then take Laplace transform both sides. So we take a Laplace transform of left side and as well as right side, which is this expression by formula. This is for Laplace transform of y prime. Laplace transform of y is the Laplace transform of little ft. Then use initial conditions, and then collect the terms involving capital Ys and other terms to the right side, and we factor the capital Ys outside. So what left here is the as square comes from there, then bs comes from there, and c comes from here, equals to this fs is still in the right side, and then you need to bring a times this s to the right, a times this k1 to the right, b times k0 to the right. So this is the terms. At this time we do not care the right side, so only I put as a stuff, and we care this polynomial, which is the coefficient of capital Y of s. Then you divide by this polynomial, so y of s equals to stuff, this is stuff, over this polynomial, which is quadratic in s, so it has cases. Now let's talk about the cases here. Ps factor, this polynomial factors, has distinct linear factors we cover in this section. So now I'm doing example below related to this first case. And for the second case, Ps is a perfect square and Ps does not factor. We'll cover in the next sections. Great. So let's talk about the first case here, Ps factors. Solve the initial value problem. This is the second order linear differential equation with constant coefficients, which is y double prime plus 4y prime plus 3y equals to e to the power 2t. Given initial condition y0 equals to 1, y prime 0 equals to 2. And the solution, first take the Laplace transform both sides. Laplace transform of y double prime plus 4 times Laplace transform of y prime plus 3 times Laplace transform of y equals to Laplace transform e to the 2t is 1 over s minus 2. And then the next, put the initial conditions and simplify, collect the transform term to the left side and non-transform term, or the terms not involving capital Ys to the right side. So we have this one here. So then, and divide by these polynomials, and then I said this is a factor case. So now Ps factor means now these factors we can factor, and then divide both sides by this polynomials, that the two factors. Then what do we have? We have down here. Let me scroll up. down, sorry. So capital Y of S equals to, we have S plus 6, S minus 2 plus 1 over S plus 3 times S plus 1 times S minus 2. Use partial fraction technique. So A over S plus 3 plus B over S plus 1 plus C over S minus 2. And now our goal is to find the value of A, B, C. These are the constants to be determined. So then again, there are many ways to find the values of A, B, and C. I substitute S equals to minus 1, I substitute S equals to 2, I substitute S equals to minus 3, and I got B equals to 7/3, C equals to 1/15, A equals to negative 7/5. Then I substitute those values back on here. So capital Y of S equals to A value, B value, C value. Then finally, let's recover the solutions in our time domain. So let's take inverse Laplace transform. So little yt equals to negative 7/5. Inverse Laplace transform of 1 over S plus 3 is e to the power negative 3t plus 7/3. Inverse Laplace transform of 1 over S plus 1 is e to the power negative t plus 1/15. Inverse Laplace transform of 1 over S minus 2 is e to the power 2t. Great. We finished this example 6. Now let's move on for example 7. Oh, that's better. Solve y double prime plus 9y equals to e to the t. Initial conditions, y0 equals to 0, y prime 0 equals to 0. The solutions, the idea, take Laplace transform both sides. So the Laplace transform of y double prime is here to here, then plus 9. Laplace transform of little y is capital Y of S equals to Laplace transform of et is 1 over S minus 1. Put initial conditions. Then what I have on the left side, capital Ys, S square plus 9 equals to right side as it is 1 over S minus 1. Then capital Y of S equals to 1 over S minus 1 times S square plus 9. Take the partial fractions. For the linear factor we use constant, for quadratic factor we use the linear terms. So here A, B, C are constant to be determined. Then we found A is 1/10, B and C both are negative 1/10, and we put the value back here, and then this is as it is. So here we distributed here negative 1/10 S over S square plus 9 minus 1/10 1 over S square plus 9. Then to apply the formula, let me scroll down. Then to apply the inverse Laplace transform, we need to manipulate this last terms. So for the first one, no problem. So little yt equals to 1/10. Inverse Laplace transform of 1 over S minus 1 is e to the t minus 1/10. Inverse Laplace transform of S over S square plus 9 is cosine 3t minus 1/10. We multiply by 3 and divide by 3, so that this 3 times 10 is 30, so negative 130. Then inverse Laplace transform of 3 over S square plus 9 by formula 7 is sine 3t. So great. So we find the solution of this given second order linear differential equations with these initial conditions. Awesome. So we finish these sections. Now in the next lecture we'll study the translations theorems. Thank you.